All right, chapter 24, amines. Chapter 24.1 is the nomenclature, the naming of the compounds. Again, you should do that on your own. OYO, that can be our acronym instead of YOLO. OYO on your own. What I do want to pick up talking about is structure. So I'm going to do structure and properties together. This is 24.1, 2, 3, and 4. We'll talk about acidity and basicity here in a minute. I've already put that table up so we don't have to go through the boredom of creating it. Now, the structure. The structure of amines, I hope you recall. And we'll just take trimethylamine as an example. We would call this structure pyramidal. Pyramidal, that's a pyramidal structure. So the nitrogen and the atoms. Now if we look at it electronically, okay, 2, 4, 6, 8 electrons, because the lone pair's there, we would say that it is sp3 hybridized and electronically is tetrahedral. Okay? So make that distinction between the atoms here and the electronics. Now, one of the key things to remember about amines, maybe you remember this from ammonia, from general chemistry, is that they undergo the umbrella inversion. That is, the substituents go up and down, and they go through a transition state that is trigonal planar. That would have a p orbital there. Those two electrons would still be in it. This, of course, for the amines is the transition state for most of them. Except we know that some get caught in that transition state, like pyrrole. Right? You remember pyrrole from the chapter on aromaticity. We'll come to that in a minute. It's going to all come together now. This comes about because the methyl groups can swing up, and as they move up we come to a trigonal planar structure, and then we would continue through that plane with the inversion of the substituents. And again, there's the lone pair. The lone pair has gone through the plane and is on the other side of the nitrogen there. So that's the umbrella inversion. And then, of course, the other thing that impacts the property of amines is when we have, say, R2NH, where we have any of the NHs, we have both a hydrogen bond donor here in the hydrogen attached to a heteroatom and in a lone pair, and so you can imagine these things lined up, hydrogen bonding to each other, creating a network in 2 and 3 dimensions. Of course, there are 2 more substituents on each of those nitrogens, and that hydrogen bonding obviously impacts the melting point and boiling point of these compounds. All right, so the other key property that we want to be very aware of here, and it's very important for our study of amines, is the basicity. And I have a table here for us already laid out on basicity, and I've combined sections 24.3, the fundamentals about basicity, with 24.4, which has to do with aryl amine basicity. So the baseline here, of course, is ammonia. Ammonia as a base. The pKa, I've just rounded these off to 1 digit. Your textbook has them to 2. You can look it up if you need that third significant figure. 9.3 for ammonia. As we add alkyl groups, we'll see that it becomes more basic. A primary amine, ethylamine is our example here, is 10.8, so that's 1.5 pK units. All right, so that's 10 to the 1.5 more basic. Now that I've started to talk about this, let me clarify what is going on. Again, remember, what we're looking at is the pKa. And even though we're looking at the bases, we talk about the pKa of their conjugate acids. So for ethylamine, we would have this ethyl ammonium cation, and we're looking at its dissociation into H+. So this is the pK equilibrium that we're looking at. Here's where Ka would be found. So it's the dissociation from the ammonium. Now that's different than, for instance, deprotonation of NH3, right? If we go the other way to NH2 minus plus H+, now that's a much, much stronger base. Remember, around 32, 33, 34 is the pK. So what we're talking about here is the acid equilibrium from the ammonium, okay? Now, we go to a secondary amine. It's a little more acidic, about half a pKa unit. That's 10 to the 0.5. Triethylamine comes back down a little bit because sterics are now involved with the tertiary substitution of the amines. Now, if we go from alkylamines to arylamines, it's very important. Of course, there's a lone pair on nitrogen, and that lone pair can be delocalized into the ring, for instance, like this. And so the impact of that substituent in the para position or the ortho position can be very important and have large impacts on the pKa. So the baseline here is just simple aniline at 4.6 for the pKa. If we put a strongly electron donating group on it, we see that it becomes more basic. Now remember, it's more basic. That means this is a better base and the equilibrium shifts toward the left side. Why is that? Well, the oxygen is electron donating, right? And so it could push electrons in and it would stabilize that protonated form here by pushing electron density over to that ipso carbon. You should draw those resonance forms so that you see it clearly. If you have questions, come reach out to me during office hours and I'll work on them with you. Likewise, remember the nitro group? It already has a plus charge on the nitrogen, so we put a plus here and we protonate this and put two pluses. Is that stabilizing or destabilizing? Of course it's destabilizing because like charges repel. So the nitro compound doesn't want to be protonated, so it wants to give up the H+, the proton, the acid, and shifts the equilibrium to the right, and we see that it is significantly more acidic. And so these are the standard electron donating, electron withdrawing effects that we can rationalize very easily if we understand the equilibrium.